Okay, this is 10.2 single slit diffraction. So in chapter 9, we looked at Young's double slit interference pattern, and we saw that we could measure the wavelength of light by doing two slits and having the two sources of light interfere with each other. And it turns out that actually, even if we just use a single slit and we send light through that single slit, we get an interference pattern that looks kind of similar. And the reason for that is that the light is actually interfering with itself as it goes through that slit. So we're going to be looking at this phenomenon. It's called single slit diffraction, and what we're going to put here is we're going to say when light passes through a small opening, and we're going to say that opening has a width of W, width equals W, it interferes with itself. The light interferes with itself. And that's because each point of light going through that slit acts as a separate source. And so if we have several of these sources all beside each other, well, they're going to be all creating new sources that are going to end up interfering with each other. Okay, and so we have below, we have a few pictures. The first picture there is a picture of this sort of interference. That picture is actually called Fraunhofer diffraction, and it's circular, but the idea is if you have a light going through sort of a pinhole, then you get this circular diffraction pattern. That is just from the single slit, the light going through a single slit. We have another picture here. This is a picture of these sorts of single slit experiments. You can see that we have the light going in, and that the light is then diffracted, and we get an interference pattern that looks like this. And notice we have our light bands here, light band, light band, light band. We have dark bands in between. Okay, and we're going to be getting into these other pictures and what they mean in a few minutes. So when we have this sort of interference, again, we have constructive and destructive. So we have our light bands and our dark bands. Our constructive interference looks like this. W sine theta is equal to m plus 1/2 times lambda. So this is the angle for the mth light fringe where m equals 1, 2, like that. So that's the mth light fringe. And our destructive interference looks similar. We have W sine theta is equal to just n lambda. And again, this is the nth dark fringe, where n equals 1, 2, like this. And notice neither of those have a 0. At the center of this situation, we do have a light fringe, but notice that if you look in the picture down here, our light fringe is twice as wide as the other ones. The center fringe is twice as wide. And we'll get into why that is, or sort of what the math of that means in a second. But you can notice then that our dark fringes occur at n lambda, and our light fringes occur at m plus 1/2 lambda. All right, so our dark fringe, we can sort of take the destructive interference equation and modify it like we did in the previous lesson to find the locations of these instead of the angle. So we can get yn is equal to n times L lambda over W. So that's the location of each of these fringes, and we can say that the separation of these dark fringes, the separation is delta y equals L lambda over W. So a lot of these are looking the same as our double slit interference pattern. Okay, the last bit I mentioned that our central maximum is a bit different, this light fringe in the middle, and we'll just say here it has a width of 2 delta y. So normally all of our fringes have a width of delta y, that's the spacing between these. The center one has a width of 2 delta y, which is 2 times L lambda over W. That's the width of our center fringe. Those are all the equations we need to know. We're going to take another quick look at these pictures. So again, this first picture is showing what the result looks like when we have sort of a circular hole. But mostly we're talking about our slit, our vertical hole. And so you can see that we have our incoming light, it's diffracting, causing that interference pattern. This third picture here shows the intensity of the different bands. So you can see that our center band here, our central maximum, is the widest. You can see that it is twice as wide as everything else. And you can see that it's also definitely the brightest. It has this, this highest peak. And then the brightness of our peaks goes down as we go from the center. And the other thing you can notice is that really it's just this central maximum that's twice as wide, and then the rest are just equally spaced as we go. And that comes directly out of our equation for the dark fringe location, or the dark fringe angle. So we're just talking about n lambda here. And so you can see that the dark fringe, we have one at, or we would have an angle at 1 lambda, 2, 3, 4, -1, -2, like this. And we don't have one at 0. So that means that we have light fringes in between the dark fringes. At the very center, we have one that's twice as large because we don't have a dark fringe right at the center. Okay, so that's just about all there is to say about it. I'm going to draw another picture of this just to make sure we understand what's going on. So if I draw my slit here, actually I'm going to make that just a bit larger. I'm going to make this slit a bit larger here. So like this, and like this. So the idea is that we have a few different point sources here. If our light is coming in, I'm going to just change color here. If our light is coming in as these waves here, the light's going in this direction, then when it gets through this hole here, it's becoming a new point source. But let's say we have a few different point sources in that slit. So this point source might be going something like this, and this point source might be going something like that. And you can see that those separate point sources are going to interfere with each other. And that's why we're getting these interference patterns. If we made our slit smaller, we would get less interference, to the point where if we made our slit very, very, very small, we wouldn't get any of this interference at all. Okay, we have the screen on the other end, and the result is we get a large bright band in the middle, and then we get bright bands that are about half as large as we go up, and about half as large as we go down. That's what we're dealing with, and we can say that the angle here, theta, well, we have our relationship for our dark bands. We can say W sine theta equals n lambda. That's our relationship for our dark bands. And again, W is this distance here, the width of our slit. So that's what's going on. That's our single slit interference. Hopefully that makes enough sense. The last picture here to the right is just showing you, again, sort of the distance between our bright spots here. So if our source is over here, you can see that we have our first light band. Our first light band would actually be going up like this in both directions. So this is all light. And you can see we have our first minimum. We have a light band between here and here, then we have a second dark band. So that's sort of what we're looking at. And you can see a lot of the math is shown in your textbook, the whole derivations, so that's what this picture is sort of helping you understand, is how that math is derived. But we're not going to get into that in this lesson. We're just going to use the equations that we were given. So let's try a couple problems here. The first one says, analyzing a single slit interference. So light with a wavelength of 5.4 times 10 to the 2 nanometers is incident on a slit with width of 11 micrometers and produces a diffraction pattern on a screen located 80 centimeters behind the slit. Calculate the distance of the first dark fringe from the central maximum on the screen. Okay, so we'll draw this situation here. I have my slit. I know that the width of that is W 11 micrometers. Good. And what else do we know? We know that the distance to the screen here, L, is equal to 80 centimeters. Okay, we also know that lambda equals 540 nanometers. And we want to calculate the distance of the first dark fringe from the central maximum. So we've got our screen here. We've got our central maximum. That's this guy right here. So I'll extend that a bit here. So this is our central maximum. We want to find the first dark fringe. So if we've got another light fringe here, we want to find this distance. So that's going to be our y1. If we look above here, the dark fringe location, this equation, yn equals n times L lambda over W. So we can say yn equals n times L lambda over W. That's our equation. And we want to solve for y1. So y1 equals 1 times, we've got 80 centimeters times lambda, 540 nanometers, all over our width is 11 micrometers. And we're going to have to do some unit conversions before we can solve this one. So y1 is equal to, well, a centimeter is times 10 to the minus 2 meters. 540 nanometers, that's times 10 to the minus 9. And 11 micrometers, so 11 times 10 to the minus 6. Okay, we do all of those calculations, and we get a result of y1 equals 3.9 times 10 to the negative 2 meters. There we go. That's our distance. That's all there is. Let's try the next page here. It says light with a wavelength of 670 nanometers is incident on a slit of width 12 micrometers and produces a diffraction pattern on a screen 30 centimeters behind the slit. Part A, we calculate the angular width and the absolute width in centimeters of the central maximum. Okay, angular width and absolute width. Let's draw this situation again. So we've got this here. I can say that my width, the slit width, W, is 12 micrometers. We've got the light coming this way. Here's our screen. Here's our central light band. We've got another light band like this. Okay, we want to find the width of our central light band. We're going to need this information. L is 30 centimeters. And lambda equals 670 nanometers. That's all of our information. We want to find a couple things. So we want to find the angular width. So that's going to be twice theta because we want to find the angle from the top to the bottom. So we're going to have theta and theta. We want to find 2 theta basically for our angular width. And we also want to find this distance here, which is going to be 2 delta y. Remember, delta y is the distance between dark band and dark band, or light band and light band. And that central one is twice as large, so it's 2 delta y. Good. So let's find first the angular width. So we can go back to our first page here and find our equation here for the angle to the first dark band. Let's find the first dark band because that's going to be the edge of our large center bit. So W sine theta equals n lambda. So we can say for a dark band, W sine theta equals n lambda, which means that theta is equal to the sine inverse of n lambda over W. Now we want to find the first of these dark bands. So I can fill in some numbers here. Sine inverse of 1 times my wavelength here, 670 nanometers, so that's times 10 to the minus 9, all over my width, which is 12 times 10 to the minus 6. And if I get that result here, I should get that my theta, is equal to 3.201 degrees. So our angular width is 2 theta, which is going to be 6.40 degrees. So that's our angular width. That's that part done. Now we want to find the absolute width. So we can use our absolute width well, this is going to be our 2 delta y. And let's see, we can check on our first page again for what delta y was equal to. Well, our central maximum has a width of 2 delta y, which is 2 L lambda over W. Good. So 2 L lambda over W. So 2 times, let's see, our length is 30 times 10 to the negative 2, 30 centimeters. Lambda was 670 times 10 to the negative 9. And our width was 12 times 10 to the minus 6. If we do that one here, we get our 2 delta y is 0.0335 meters. There we go. So that's our absolute width. That is our average, our angular width, and we're done. Part B says calculate the distance between the first and second minima. So the distance between the first and second minima. Well, that's just our delta y, right? First and second minima, delta y. And we have delta y, delta y is equal to L lambda over W. We already calculated 2 L lambda over W, so we could just take that value and divide by 2, but I'll write this out again. We've got 30 times 10 to the minus 2, 670 times 10 to the minus 9, and 12 times 10 to the minus 6. And that gives us a delta y of, let's see, 1.7 centimeters. There we go. So that's half of what we had before. And I could write our answer before as 3.35 centimeters. That works as well. All right, we have 1.7 centimeters. And part C, determine the distance between the second and third maxima. So the second and third maxima now, not the minima. And we want to compare this answer to the answer in B. Does this answer make sense, and why or why not? Well, second and third maxima, we can look at our equation here. We've got our location for the dark fringes. Our light fringes, we could be adding half a lambda. We could do all sorts of calculations. But we've already said all of these are equally spaced. We have a single equation for delta y. So if we're going between the second and third maxima, those are one after the other. So we have delta y is L lambda over W. And we already did our calculations for that, 1.7 centimeters. And this is the same as part B. And yes, it makes sense. Because these fringes are all evenly spaced. The only one that's not, yes, it makes sense. The only one that is not evenly spaced is that central maxima, which is twice as large. Okay, so there we go. That's the lesson. There's a few problems at the bottom there for you to try, and I hope you enjoy them.